Hey, good evening. Welcome to this Sunday night version of Live Review with learn-biology.com. It is really great to be here. I'm Mr. W, and I am so happy to be here and to be teaching Biology. It's the thing that I'd love to do best. And I wanted to make sure that I could actually be heard. So that's why I was just looking down, making sure that my microphone was actually working. You might notice that my background's a little bit different, that I'm actually you're seeing the reality, you're seeing the green screen that's actually behind me. And that's because that's usually how I do my stuff. Um, and I had a couple of technical problems that are forcing me to eschew my virtual reality. So you're getting to see the real me, the real green behind me. And, that's not a bad thing. So anyhow, really psyched to be here tonight because tonight is all about energy. What I mean by that is that we are going to be talking about all things related to energy and ecology. And if you are so able, what would be great would be to see who you are and where you're from and what brought you here tonight. So you can put that right into the comments, and that would be awesome while I sort of figure out that's where I want to be. So anyhow, let me tell you what we're going to do tonight. We're not going to be over there with biogeochemical cycles. Really, where we're going to be is way back here, way back here. Okay. Yeah, here we are. So welcome. Really great to have you here. I hope that experience just didn't cause many of you to leave, but here we are teaching live, and in live, life happens. So here we are. We're continuing our review of ecology. This is I believe, the 6th of the live review sessions that we're doing as a lead up to this year's AP Bio exam. So here's the outline of Unit 8, Ecology, which is where we are now. We talked in our last session about responses to the environment. Today, we're going to focus on energy flow through systems. Don't think we're going to get through population growth. We're going to leave that for the next section. And then there's incredible topics: community ecology, biodiversity, disruptions to ecosystems. And that is the last topic of the course. And then we're just going to spend our time reviewing for the big exam, which happens on May 16th. And I'm really grateful to those of you who are here that you chose to be here to review with me. So thank you very much for doing that. Tonight, we're going to talk about a couple of issues related to energy flow in ecosystems. And just remember, a huge amount of the course relates to cellular energetics. So in previous videos that I've made, and of course in previous lessons that you've taken, you've learned about things like photosynthesis and cellular respiration. And those are processes that happened at a cellular level mostly to generate energy for cells. Now we're looking at this at the level of entire organisms and entire ecosystems. And that's where we're going to be tonight. So the topics that we're going to deal with tonight include metabolic rate and size, food webs, trophic levels, the pyramid of energy and the 10% rule, and some other ecological pyramids. We might also look a little bit at biogeochemical cycles, including the carbon cycle. Tonight is really a special treat because I'm going to do some live music tonight. So looking forward to that. And it's going to be a great experience. So a little bit about me. My name is Glenn Wokenfeld, also known as Mr. W. I'm a retired AP biology teacher, taught AP biology at Berkeley High School for many, many years, and retired from the classroom last year so that I could do this full time. While I taught AP Bio, most of my students got 4s and 5s on the AP Bio exam, and I'm really hoping that I can be bringing the same level of success to you. Part of the reason for my success was the fact that I used this website, learn-biology.com. I not only used it, I wrote it for my students because I'm a big believer that traditional textbooks are not so good at eliciting learning. And really what you need to be doing is you need to be interacting with content and getting feedback. And that's what happens at learn-biology.com. There's an associated app that goes with it called Biomania. It's available on the App Store and the Google Play. I'll probably tell you a little bit more about that later. We're going to start with this question. What are the advantages and disadvantages of being an endotherm? So I'm assuming that everyone who's watching this show is an endotherm because humans are mammals. Mammals are endothermic. If you think about the vertebrate clade, the two subclades are the birds and the mammals, which are endothermic. What does that mean? That means that we keep our body temperature at a constant level. And that doesn't matter whatever the ambient temperature is. So you see how the ambient temperature might be 10 degrees, and we keep it at 37 degrees C. It might be 30 degrees, and we keep it at 37 degrees C. That's very different from our vertebrate relatives like reptiles who don't maintain homeostasis with regard to body temperature. If it's 10 degrees, then the body temperature of a snake will be 10 degrees. As that temperature goes up, so will the snake's body temperature, and that will continue. It's a pretty linear relationship, though snakes do have varying mechanisms that are mostly behavioral to control their body temperature. So they're not completely at the mercy of the environment, but they certainly are, they're certainly less active when it's cold than they are when it gets warm. And that's why you tend to find snakes in warm places. Well, what are the advantages and the disadvantages of being like us or the birds? Well, the advantages are that we can be active regardless of the environmental temperature. And that explains why the predominant animals in the Antarctic or the Arctic are mammals. So think of like polar bears or seals or things like that. And birds in Antarctica. Those are mostly terrestrial, but if you think about the non-fish-like animals that live in Arctic waters, those tend to be mammals or birds. Now, of course, you might be wondering, well, what about fish? Fish have a whole variety of adaptations that enable them to remain active even in relatively frigid waters. So that's yet another thing. The disadvantage of being endotherm is that it takes a lot of energy to keep your temperature up at a high level. That's particularly true when it's cold. And then you actually have to use a variety of adaptations to warm yourself up. Now, some of those adaptations are just structural. So like, for example, the wolf is covered by a layer of fur. But there's all these metabolic adaptations. So like, for example, one thing that mammals do is they shiver. And shivering is muscle contraction that doesn't generate movement. And that's how you can actually maintain heat even in the face of cold. And there's some really cool adaptations that happen among babies and hibernating mammals, like the consumption of brown fat. The respiration of brown fat is really what I should have said. And that is a kind of fat that's rich with mitochondria, and it can burn literally, I mean, maybe figuratively is really the right way to say it. It can figuratively burn calories without creating ATP. There's a whole pathway connected with that, but I'm going a little bit far afield. Here's an example of the fact that being an endotherm requires a lot of energy. An alligator requires, in terms of food energy, about 150 calories a day. That's about less than 2 pieces of bread. A human about the same size requires 2,000 calories a day. So costs and benefits of being an endotherm. And of course, you could just think about the inverse for the ectotherms. That leads us to the topic of metabolic rate. And here we see a bicyclist crossing the finish line. That's an example of metabolic rate. And what's really cool is that bicyclist is me. That's me having finished the Seattle to Portland bike ride sometime in the 1990s, a really, really long time ago. And here's a person whose resting metabolic rate is being measured. So what is metabolic rate? It's the amount of energy that an organism expends during a given amount of time. Calories per hour. That's a metabolic rate. If you're working out at the gym and you're on like an elliptical trainer, you can see that. You can also see watts. Watts is another. It's sort of measures of power. And usually, though, we measure that in measures like this: oxygen consumption, carbon dioxide production, or heat production measured during a given period of time. So this woman is wearing a mask, and probably what this device is doing is measuring her carbon dioxide output. And you can imagine that there are athletes who get on trainers and their metabolic rate is measured. There's all kinds of things. You can do this with animals too. So here's a complicated thing. We can talk about, like, for example, calories per hour. But then when you think about animals that are different sizes, how do you set up a comparison of, for example, an elephant and a mouse? Because obviously the elephant is going to burn a lot more energy, but that is not really what you need to look at. What you need to look at is this. It's called the relative metabolic rate. It's the metabolic rate per unit of body mass, and that's often measured in units like liters of oxygen per gram of tissue per hour. That's what this y-axis is over here. So that's how we're measuring it in a shrew compared to an elephant. And here's the really cool thing. Obviously, the elephant, because it's such a huge animal, is going to be consuming more oxygen. But relative to its size, per gram of elephant tissue compared to per gram of shrew tissue, a shrew is like a little mouse, the shrew is burning so much more energy. And among endothermic animals, mammals in particular, the general rule is that as size increases, the metabolic rate decreases. And that is a rule that is probably worth committing to memory. The degree to which metabolism will be on the AP Bio exam is unclear. It kind of shows up occasionally, but this is where AP Biology kind of oozes into a course that might be in anatomy and physiology. So I would be familiar with this, but if it's not your number one topic, I wouldn't worry about that too much either. But here's an example. A gram of mouse tissue metabolizes 10 times faster. It's pulling in oxygen 10 times faster than a gram of elephant tissue. And why is that? It's supposed to be related to the surface area to volume ratio. And smaller animals lose heat much more easily than large animals do. And as a result of that, to replace the heat, a smaller animal needs to perform more cellular respiration. So the shrew is just burning through energy at this phenomenally fast rate, whereas the elephant's tissue is relatively much more relaxed. It's burning through much less energy. And here's some things that relate to this kind of metabolic scaling. So per calories per day per gram for an elephant is way less than 1, whereas for a shrew, it's about 80. So it's 1,000 times more in the shrew. And that shows up in all these other really cool facts, like the Etruscan shrew. And here's a shrew that's resting on someone's thumb. That's how small that animal is. There's my thumb. So imagine a little animal resting on my thumb. That's how small it is. Its heart rate is 1,200 beats per minute. It breathes 800 times per minute. If you have it in a situation where it doesn't have any food, it'll starve to death in about 4 hours. And it eats 200% of its body weight every day. Let's say that I weigh 190 pounds, which is about close. That means I would have to eat 380 pounds of food per day. I don't eat that much. That's crazy. That would be if, my tissue were burning energy at the same rate as a shrew. And just for comparison's sake, here's the elephant. Its heart rate is beating 30 times per minute. Elephant's a lot bigger than me. My heart rate's about 50 times a minute. Relatively fit 62-year-old man. Elephants only breathe 4 or 5 times per minute. An elephant, like any large animal, can go for many days without food, and every day it takes in about 4% of its body weight. So this is the whole issue. I'm just going to jump back to it, of metabolism as it relates to size. So something to store away in your basket of knowledge related to AP biology. So now that we've talked about energy flow through individuals, now we're going to talk about energy flow through ecosystems. I want to emphasize that while I definitely have a show to provide and material to cover, the most important thing that I like to do in these live shows is answer questions. So please, at any point, use the YouTube comment feature to just throw a question in, and when I get to a good moment, I'll stop and I'll answer it. So thank you very, very much for just being here and watching. I'm honored that you're here spending your time with me. But I want to emphasize, the most important thing that's on my agenda is answering your questions. What's food chain? Food chain shows the passes of energy and matter from one organism to the next within an ecosystem. A food web shows all the interconnected food chains. So here's a food chain: land plants to small mammals to large mammals to top carnivores. But when you put all of the food chains in an ecosystem together, that's when you have a food web. And this is a fundamental ecological concept. This is how energy flow is structured through ecosystems, through food webs. Trophic levels are an organism's position in the food chain. And the ones that you need to know about include producers, down here at 1. This is for a terrestrial food chain, and this is for a marine food chain. They create energetic organic compounds almost always through photosynthesis. That's what producers do. Primary consumers, or herbivores, they eat the producers. So if you're a vegetarian, you could be a primary consumer. But if you are a carnivore, then eating meat, then you'd be a secondary consumer or a carnivore, and that means that you would eat the primary consumers. And of course, humans are omnivores. We eat at both levels, and sometimes we're even tertiary consumers. So like, for example, tuna is way up high in the oceanic food chain. So if you do something, which many people do, like eating a tuna fish sandwich, that puts you way up in terms of trophic levels, because the tuna's eating something that's eating something that's eating something. So that might make you a 4th or a 5th level consumer. In some oceanic food chains, excuse me, there might be as many as 5 trophic levels. When organisms die, their remains are broken down by decomposers, and that's not shown in this system. So in relationship to ecology, there's 2 important ideas that are represented in this diagram. One is the pyramid of energy, and the other is the 10% rule. And the pyramid of energy shows the amount of harvestable chemical energy in trophic levels. What does that mean, harvestable energy? If you were to collect every part of every producer, so like all of the grasses and the herbs and all of these little wildflowers and things like that, you could actually measure the chemical energy that's present in all of those organisms. You can use a device called a calorimeter, where you would burn it and you'd actually see how much chemical energy is present. And then you could do the same with all of the primary consumers. Sounds a little grisly when we talk about doing that with a bunch of animals, but that's what we do. We would take all the primary consumers, we'd measure their energy, and then we would do the same thing with the secondary consumers. Well, what we find is that each trophic level has 10% of the chemical energy of the level beneath it. So in this example, we have 10,000 kilocalories, which is really an absurdly low amount of energy represented, but just for ease of math, if this is 10,000, well, then 10% of that, 1,000 kilocalories, or whatever unit you're measuring, would be present in the primary consumers. The secondary consumers would have 1,000 calories, and the tertiary consumers would have only 10. So you're losing 90% of your energy. Now, why? I'm going to explain that with a song. So what I'd like you to do is this. I actually can't open this link directly because in the software that I use, bad things will happen. So what I'm going to do is I'm just going to grab that and I'm going to go like this. And good, you're still seeing it. And then I'm going to go like this. Thanks for your patience with me here. And then I'm going to go like this, just so I can make sure that I get back to it. So I'm grabbing this, making a little note, Unit 8. Fantastic. Okay, so here we are. So I want you to go to learn-biology.com/food chains. Like literally, I want you to type that into your browser bar right now. Oh, I guess I could put that right here. Okay, so you can see that in the comment that I left for you. And what I'd like you to do is go there. And if you do go there, you'll see this. So now we're on learn-biology.com, my website, and you're on a page related to the music videos. I don't know if you know this about me, but like in addition to the fact of me being an AP biology teacher, I also have the Science Music Videos channel where I make musical representations of songs. So this is a song that I made a really long time ago. And the reason why I asked you to come here is that this way you can see the lyrics to the song and I can see them too. And I'm going to make them a little bit smaller. And that is going to enable me to do something really fun. So I think I'm going to leave that the way it is. So that way, if you just wanted to read it on the screen, you could do that too. And I'm going to push my chair back. And then you're going to see something that you might not have seen your biology teacher do before. I'll take my guitar. And that's going to set me up to do one of my favorite things in the world. Which is to sing about Biology, my favorite subject and my favorite way. So let's go like this. Yeah, that'll work. You should be texting all your friends right now and saying, hey, the guy who's teaching this review session for AP Bio, he actually just pulled his guitar out and he's going to sing a song. And that would be kind of fun. I might actually do this again. So the purpose here is to explain food chains. And this is not an original song. Almost all my songs are. This is to, there was a TV show in the 60s called the Beverly Hillbillies. And I took that tune and I made that into this song about food chains. And I did that on about the second day I was ever a teacher. And that was incredibly long ago, so long before you were born, undoubtedly. But the tune goes like this. Oh, a nuclear reaction happens deep inside the sun when hydrogen absorbs into helium. Then the heat and light is radiated into space, and 90 million miles it shines upon the Earth's face. For every 100 calories that shine up from the sun, the calories that green folks trap will number only one. But every single calorie in ocean, hills, and plains will serve as a foundation for a living food chain. At the bottom of a food chain are producers like green plants, whose cells make food from sunlight they can use to chloroplast. Happens in the pines and flowers on your windowsill, because every single green plant's got a little chlorophyll. Well, the next step in a food chain is a primary consumer, an herbivore, a cow, or vegetarian baby boomer. Primary consumer spends its mealtime eating plants. Might be a buffalo or might be an ant. Each level in a food chain yields only 10% of the former level's energy. You might as well when there are bones and leaves you can't digest that really make a dent. And don't ignore the weight it costs the metabolic rent. So if your plants are yielding about 100 calories, your yield will only be 10 in the birdies and the bees, 700 calories in algae in the sea. In primary consumers, it will yield you 70. Some other ways of getting food are really out of sight. You could be a predator or be a parasite. Predator eats meat, a parasite eats your insides, and if you're a decomposer, you will leave me when I die. And if you know this about food chains, you can really take the cake. When energy goes through, it doesn't last, it dissipates. But nutrients and food chains meet a very different fate. They recycle and they circulate forever. Ain't that great? Just remember, there's no beings in this world that make their home. Populations form communities where all do make their home. Though your niche may be determined in the role that you are playing, every creature alive or dead is in a food chain. All right, that is the food chain song, and for AP Biology, that explains everything that you need to know about trophic levels and food chains. Fairly extraordinary stuff. So let me just emphasize a couple of points by going back to where we were before. And let's just see if we can do that by going like this. And there we are. Beautiful. Now we're going to go back here. Okay, so why is there so much loss of energy between these food chains? Well, there's a couple of things that you should know. First of all, if you think about, like, for example, rabbits or other primary consumers, they don't eat every last shred of the level below. I mean, some herbivores are actually quite voracious and can really practically denude an environment. But even then, they're not taking like the root matter and stuff like that. If you think about a goat, which are brought into my part of the world to do fire prevention because they'll eat all the shrubbery. Well, so there's all of these roots and things like that that don't wind up passing through. The other thing is that even of the stuff that, like, for example, this rabbit does take in, it can't metabolize everything. You wind up literally pooping out a lot of it. So we've got inefficient harvest, we've got inefficient energy conversion, and then the last thing that we have is this. Last thing, the third reason is entropy. Whenever there's a conversion of energy from one form to another, there's some loss as heat. So if you can hold on to those three ideas, then you'll be in great shape. So Sophie, thank you so much for those applause. It really means a lot to me to see that. Thank you very, very much. So that is food chains. Another system that we're going to look at now, is we are going to look at the Calvin cycle. We're going to look at biogeochemical cycles. And let me go like this. Okay, so biogeochemical cycles, honestly, I'm not certain the extent to which they are or are not part of the AP curriculum. They certainly have been in previous years. They don't figure prominently in the College Board's course and exam description. But in terms of just knowing the basics, biogeochemical cycles show the movement of elements or compounds between the biotic and abiotic parts of an ecosystem. Biotic are the living parts, so the organisms, and the abiotic part are the non-living parts. And there are reservoirs where substances are stored, and then there's fluxes that move material from one area to another. So what I want to do for you now is play you another song. This one I'm actually going to let the video do the work. So we're going to go to here. So just watch this.
I'm a carbon atom in a CO2 up in the air. In the air, in the air. Floating with the oxygen and nitrogen up there. Nitrogen and oxygen up there. There I'm gonna be until I'm sucked into a tree. Into the leaves of a tree. Photosynthesis captures me. Puts me in the leaves of a tree. Fixed to the leaves, I'm in a new situation. Now I'm a solid in a plant location. Cause photosynthesis does carbon fixation. Carbon fixation. Carbon cycle moving me around. Gaseous in the air and solid on the ground. Carbon cycle going round and round. Going round and round and round. I might be fixing to a tree or herb, a weed or shrubbery. Maybe an algae floating in the sea. But after CO2 enough produces where I'll be. Producers where I'll be. Formerly a gas, now I'm a solid carbohydrate. Leaves of bark and fruit and wood are mostly carbohydrates. Or possibly a grain of rice on someone's dinner plate. Someone's dinner plate. Then maybe I'll be eaten by a deer or mouse or bird. Chewed by a goat or by a buffalo herd. After being swallowed, I could be dropped as a turd. Dropped down as a turd. Carbon cycle moving me around. Gaseous in the air and solid on the ground. Carbon cycle going round and round. Going round and round.
Hey, I just had a thought that makes me very nervous. And Sophie, I know that you're out there. Is there any audio coming through, or is that silent? Very nervous that it might be silent. Sophie, were you able to hear that? Can we go into my, oh, there is. Lily, there is audio. Fantastic. I'm going to play the rest.
In a plant or animal, I might get respired. For energy, I'll get respired. CO2's released and oxygen's required. Oxygen's required. Or possibly it carries me before fall to the ground. Onto the soil on the ground. Decomposers break me down and CO2 comes out. CO2 comes out. Decomposition, respiration put me in the air. Carbon dioxide in the air. With the clouds of nitrogen and oxygen up there. Nitrogen and oxygen up there. Carbon cycle moving me around. Gaseous in the air and solid on the ground. Carbon cycle going round and round. Going round and round and round. Or maybe I fall to the ground, no oxygen around. Lots of things accumulate pound by pound. Makes me into fossil fuels deep under the ground. Deep under the ground. You mind the coal and oil and gas combust me in machines. CO2 emitted from machines. Now the CO2's at levels no one's ever seen. No one's ever seen. Carbon cycle moving me around. Gaseous in the air and solid on the ground. Carbon cycle going round and round. Going round and round and round. Carbon cycle moving me around. Gaseous in the air and solid on the ground. Carbon cycle going round and round. Going round and round and round.
Okay, thank you very much. So now what I'd like to do, unless there are any questions, is I would like to take us to learn-biology.com, where we can do some multiple choice practice. All right, so I hope that sounds good to everybody. I think that when I do this, I get a little, okay, yes. Fireworks, fantastic, love that. Okay, so I'm gonna do this. No, not gonna do that. I'm gonna go here. Oh, I know how to do this. I'm just gonna go here. Courses, AP Bio, I shouldn't have done that. I'm gonna go to AP Bio Review. And let's do some multiple choice review. And there are multiple choice. And just want to emphasize that, like what we're doing a tiny bit of tonight, if you have an account on learn-biology.com, and I know some of you in the audience do, and I'm really, really grateful to you for doing that, then you can do exactly what we're going to do. So you just click Start Quiz. Well, I think I need to log in. Here I am. Fantastic. Am I in? Fantastic. Okay, so I want to focus on ecology. So I'm going to click ecology and actually want to drill down a little bit more. I'm going to just do energy flow through ecosystems. And we've got 15 questions to practice with. Yeah, so that's what we're going to do. Okay. That is pretty small. Wondering what I can do to make that bigger. I made it smaller. I go like that. That's pretty good. Okay. So diagram below represents the carbon cycle. Which number would represent a cow eating grass? Love to see some answers in the chat. A cow eating grass. All right. See one answer? All right. We're going to click on number 4. Terrific. Number 4 shows carbon moving from plants to animals. And that's what happens during ecological consumption. Ooh, this is going to take some tough analysis. Which organisms in this food web are both secondary consumers and tertiary consumers? So we've got hedgehog and hawk. We've got badger and fox, badger and fox. We've got fox and hawk. We've got the hawk only or the fox only. So we're looking for a secondary consumer. 1, 2, 3, 4, 5. Those are the answers. Okay, it looks like we've got 2 people who are really participating, and I totally appreciate that. Which organisms are secondary consumers and tertiary consumers? All right, so we've got 4 and a 3. I'm going to go with 3, fox and hawk. Okay, way to go. The fox and the hawk are the tertiary consumers in this food web, and they're also secondary consumers. So let's look. Fox, it's a secondary consumer, but a fox is also a tertiary consumer by that route over there. And a hawk is a secondary consumer when it eats a rabbit, but it's also a first primary consumer, secondary, tertiary consumer through this pathway over here or through this pathway over here. Okay, so that's how that one goes. Okay, a comparison of energy consumption in mammals of various sizes would show that, folks, take a look and read and tell me, is it 1, 2, 3, or 4? You've got 4 choices. One, two, three, or 4. What do we got, folks? Okay, we've got a 1, we've got a 1. As mammals increase in size, they consume more energy. At the same time as mammals become larger, each gram of tissue will require proportionally less energy. That's correct. A larger mammal, I didn't show you this diagram over here. A larger mammal will consume more energy than a smaller one. That's the graph on the left. However, as shown on the right, its tissue-specific metabolic rate is much lower than that of smaller animals. And I would, Sophie, Lily, I mean, you already get it, but I would be familiar with these 2 graphs because they really tell what you need to know about metabolism. Let's look at another question. Which of the following statements best describes energy in an ecosystem? We've got 1, 2, I'm sorry, 1, 2, 3, or 4. What's our response here? And we've got choice number one again. 10% of the energy is lost as it moves from producers to herbivores and from herbivores to secondary consumers. Let's see. No, it's not 10% is lost. 10% is transferred. 90% is lost. Study the diagram below. How much energy is lost between trophic levels? So this is the beauty of learn-biology.com. If you get an answer wrong, no big deal. You get a hint about what the answer is, and then you get to try that question again. So it's the kind of feedback and interaction that leads to learning. And that's why, if there are any of you who haven't yet purchased a subscription to learn-biology.com, free trial period ended about a week ago. So you have to purchase, it's $24.95. Then this is the kind of feedback that you get. Let's go on, let's do some more. A team of biologists, this is a term I didn't go over tonight. Let's see how well you've been learning vocabulary, either on learn-biology.com or from your teacher, wherever you are on planet Earth. A team of biologists studying geothermal hot springs has discovered a prokaryotic organism in a light-free zone deep within the pool. Metabolic analysis shows that this organism gets its energy by oxidizing hydrogen gas, H2, and using it to reduce carbon dioxide gas into a variety of carbohydrates. The best classification of this organism would be is it a photoautotroph, a chemoautotroph, a heterotroph, or a lithotroph? What do we got here? 1, 2, 3, and 4. And we have two choices for chemo, autotroph, and Ohad, welcome, welcome, welcome. It's great to have you here, and thanks for chatting in. Let's try chemo autotroph. Fantastic. A chemo autotroph feeds itself. That's what we're seeing here. Powering the reduction of carbon dioxide by gaining energetic electrons from some inorganic source. So it's oxidizing hydrogen gas, using it to reduce carbon dioxide into a variety of carbohydrates. This is really cool because it's this kind of metabolism that was present at the origin of life, probably in some hydrothermal vent deep underneath the sea 3.8 billion years ago, and still happening today. Okay, so here's some analysis that you might have to do. And just so that you know, all of these questions are original questions, but I've tried to base them as much as possible on questions that you might experience on the AP Bio exam from the College Board. And so that's, again, the value of doing this work on learn-biology.com. And I'm super glad you're doing it with me tonight. But I just want to emphasize, as the AP Bio exam comes up, you're going to want to spend your time doing this. So movement of carbon among components of a freshwater aquarium. Which number represents photosynthesis? Okay, so you're just identifying the arrow that represents photosynthesis. And I'm seeing many choices for number 2. Let's try it. Fantastic. Number 2 shows carbon moving from the water in carbon dioxide into plants, and that's carbon fixation, and that's what happens during photosynthesis. Oh, here's another question like this. Which number shows carbon moving from a lower to a higher trophic level? And Jennifer, welcome. Thank you for chatting in. Let's see our answer to this. 2, 4, 5, 6, 7. See the answers, folks. And Seeing a bunch of choices coming in. Carbon moving from a higher to a lower trophic level. And let's see what happens. I'm going to choose 5. Okay, now let's see what's going on. Here we have carbon in microorganisms. So the carbon in plants is flowing to the microorganisms. The carbon in the snails is flowing to these microorganisms. And then they're producing carbon dioxide in the water. That's decomposition. What you're looking for is the process that moves matter and energy from a lower trophic level, like producers, to a higher one, like consumers. See if you can find one in the diagram below. So in the diagram below, that would be respiration. So what number would that be here? If we have time, we'll cycle through this question again. Okay. The image below shows a food chain. This would not be an AP question. This is way too easy to be an AP question, but not bad practice. The term that best describes the caterpillar's ecological role. Is it a producer, a primary consumer, secondary consumer, third level consumer? 1, 2, 3, or 4. Let's see it, folks. Everyone's nailing this one. Indeed, it's 2, producer, primary consumer. Well, what did I sing? Okay, I'm trying to remember the words to the food chain song, and it's failing me right now. But anyhow, it's a primary consumer. Let's see. Excellent. The caterpillar is a primary consumer. The diagram below represents the carbon cycle. Which number represents respiration by plants? Tricky diagram. I've got it about as big as I can make it. Respiration by plants. Let's see a number. So what we see over here at number 2 is carbon in green plants, and then there's respiration that's returning atmospheric carbon dioxide. 2 indeed is the answer. And this is an important thing to remember because this is often a stumbling block for AP Bio students. Plants do respiration and photosynthesis, whereas animals are just doing respiration. So important to know that, like during the nighttime, how are plants staying alive? They're doing respiration. During the winter, how are plants staying alive? Respiration. But plants are also doing respiration during the daytime to power all the metabolic processes that are happening in their cells. So just, photosynthesis happening in chloroplasts, creating sugars, and then those sugars are used in respiration to power all the processes that are found in plants. So plants do both respiration and photosynthesis. Okay, this is really the same question. It's so easy. I'm going to answer it myself. Oh, no. Secondary consumer. Who's a secondary consumer? 1, 2, 3, or 4? Okay, people are crushing it on ecology. And, ecology in some ways is one of the, at least at this level, this kind of stuff, it's not the hardest stuff in AP biology. Not to take anything away from you and your achievement so far. Why do endotherms require much more food than ectotherms? 1, 2, 3, or 4? What do you think, folks? And beautiful. You might know this from previous knowledge. You might know it from what I talked about earlier on in the chat, but ectotherms require less energy for their metabolic processes. That is indeed the answer. They don't regulate their body temperature. They require less energy for their metabolic processes. Okay, finally, a tough question. Based on the graphs below, which letter or number indicates the basal metabolic rate of an endotherm? Endotherm. So I'm just going to have you think that through for a minute, and then I'll explain it. All right. The basal, just think the basic, the fundamental metabolic rate. And what we're looking at is the relationship between temperature and metabolic rate. So which one of these would apply to an endotherm? Toughest question we've had all night. Is it A, C, D, E, or F? And you can actually put a letter in for this one. I can tell everyone's thinking. This is a tough question. Okay. So let me explain this a little bit. The basal metabolic rate is the rate that you would be consuming oxygen when you're neither in cold stress nor in heat stress. So, first of all, let's note a couple of things. We can eliminate everything in graph 2 because this is obviously obviously the metabolism of a reptile. When it's cold, its metabolic rate is low. I mean, a reptile, an amphibian, a fish, an ectotherm. All right. So when it's cold, the metabolic rate is low. And as the temperature goes up, the metabolic rate increases. So eliminating we're eliminating this over here. Now, over here, this is obviously the metabolic rate of a mammal or a bird. Why? Because when it's cold, ambient temperature is low, the metabolic rate is quite high. Well, that's the truth. If you ever go up to, in the wintertime on a cold day, it takes a lot of energy to maintain your temperature at 37 degrees. You have to actually burn energy to do that. As the temperature increases, it takes less energy for you to maintain your body temperature. At a certain temperature, which I think is about 80 degrees or 70 degrees, it doesn't take any energy at all for you to maintain your body temperature. That's your basal metabolic rate, and it's represented by this line over here at D. That's why I kind of had to leave B off the graph, right? So this line represents the basal metabolic rate. And then as it gets really hot, then you actually have to expend some energy for cooling. So the answer is D. D shows the basal metabolic rate of an endotherm. So D, actually D, Lily, D, Sophie, D. So that's what we got going on. So fantastic work. Good job. Way to go. Really proud of everybody. So it's 6:57, and we're going to do a couple of things that we usually do at the end of these sessions. One thing we're going to do is we're going to go back. No, that's not going to do the trick. We're going to go to our slideshow. That's not going to work. Thanks for your patience with me while I figure this out. Okay. So okay, fantastic. So here we are. And to end, I just want to talk about how you can set yourself up for a 4 or a 5 in AP Biology. The first thing is I've got a really great AP exam checklist that goes with a video that I just released. I just released a speed review. If you go to the Science Music Videos channel, you can see my speed review. I should have embedded it into the slideshow. But just Science Music Video Speed Review. It's my latest video that I'm releasing another one tomorrow. And it's designed to be used with this checklist. Download the checklist and then just like go through the checklist. What do you know? What do you not know? And it has links to all the tutorials on learn-biology.com, because what you want to do as part of your AP review process is you want to find the gaps in your knowledge and you want to fill them as quickly as possible. That's really what the checklist and learn-biology.com are for. And then every unit has a review page, and each review page has flashcards, multiple choice quizzes, practice FRQs, click on challenges, so that you can really master the material in that unit. The other thing I want you to do is please continue to attend these live review sessions and spread the word. The next one is going to be on Wednesday. Can't do tomorrow night, can't do Tuesday night, but I'll be back with you on Wednesday night, which is the 24th. Please sign up for learn-biology.com. I'm going to make an announcement right now. I'm going to start accompanying these YouTube lives with exclusive review sessions on Zoom, because Zoom is really a much better it's much better setup for this kind of teaching. You know, we won't have the latency and stuff like that. So you have to be a subscriber, and you got to sign up and go to learn-biology.com/apbio. A monthly subscription is $24.95. It's incredibly cheap for the value that you get. And you'll get access to these Zoom sessions, which will happen like once a week or something like that, but it'll be much more effective. I'm going to cap the size of those sessions to about 30 people. So first 30 people who sign up get into the first cohort. I might open up other cohorts, but that's how we're going to start this thing off. So that's how you're going to set yourself up. You've got everything you need to set yourself up for AP Biology success. You also get access to the Biomania AP Bio App, so you don't have to buy that separately. You just have to get the Learn-Biology. And next review session, Wednesday night on the 24th. So it's 7 o'clock. I have had so much fun being with you. You guys are awesome. I feel like I'm working with heroes, because you are on a mission. Your mission is to get to AP Biology success. So thank you so much for joining me tonight. I'll see you again on Wednesday. Tell your friends, tell everybody. I'll see you here. I think this one's on 7 p.m. I hope I didn't send an incorrect message about the time, but thank you all very, very much. It was really fun to be with you tonight, and I'll see you again on Wednesday. Everybody be well. Take it easy. Be safe.